Welcome to the fascinating journey of dairy and food engineering in India. Today, we explore how the dairy sector evolved from colonial times to a modern powerhouse. The story begins with British military dairy farms established in 1913, aiming to supply milk and butter to the army. These farms used improved milch animals and some herd improvement practices, but their impact on civilian consumers was limited. As urban populations grew, milk vendors became the primary source for city dwellers, leading to environmental concerns and genetic drain of superior cattle breeds. This set the stage for a transformation that would change the face of Indian dairying forever. Urban milk vendors kept cattle in cities, selling milk door to door. This led to the rise of cattle sheds across urban centers, causing environmental problems and contributing to the depletion of genetically superior breeds. Vendors focused on maximizing profits, often extending lactation periods, which resulted in sterility issues among high-yielding cattle. Once unproductive, these animals were sold to slaughterhouses, further draining the country's valuable livestock resources. The lack of organized systems for milk procurement and quality control meant that urban consumers faced inconsistent supply and quality. The Second World War brought momentum to private dairies, introducing modernized processing facilities in major cities like Bombay, Calcutta, Madras, and Delhi. Brands such as Paulson's, Kevinters, and Express Dairy pioneered urban milk processing, offering processed milk, butter, and ice cream, albeit on a limited scale. Despite these advancements, the focus remained on profit rather than breed improvement or organized production. The dairy sector continued to be fragmented, lacking a cohesive structure to support both producers and consumers. After India's first five-year plan in 1951, the government prioritized modernization of the dairy industry. Milk schemes were established in large cities to provide hygienic milk to the growing urban population. Programs like the Integrated Cattle Development Project, ICDP, and Key Village Scheme, KVS, aimed to stimulate milk production. However, without a stable and remunerative market for producers, milk production remained stagnant, growing at only about 1% annually between 1951 and 1970. The lack of rural procurement systems and reliance on contractors and middlemen further hindered progress. Government dairy plants often extended buffalo milk by reconstituting imported milk powder, aiming to lower prices. This led to decreased domestic production and the establishment of cattle colonies in cities like Bombay, Calcutta, and Madras. These colonies contributed to environmental degradation and caused a genetic drain on rural milch animal populations. Rural producers received little incentive to increase production, while urban demand continued to rise, highlighting the need for a more organized and sustainable approach. The late 1960s marked a turning point with the establishment of the National Dairy Development Board, NDDB, in 1965. NDDB was created to promote dairy cooperatives, finance infrastructure, and provide technical support. Operation Flood, conceived by NDDB and endorsed by the government, aimed to enhance milk production, increase rural income, and ensure fair prices for farmers. The Indian Dairy Corporation, IDC, was established in 1970 to handle project funds and commodity management, while NDDB provided technical support. Operation Flood's first phase, 1971-980, was financed by the sale of skimmed milk powder and butter oil gifted by the European Union. The program organized dairy cooperatives at the village level, created infrastructure for milk procurement, processing, and marketing, and established dairies in major metropolitan cities. 18 premier milksheds were linked with consumers in Bombay, Calcutta, Delhi, and Madras, laying the foundation for India's modern dairy industry. Phase II, 1981-85, integrated state-level dairy development projects into Operation Flood. The World Bank provided significant funding, and commodity assistance from the European Economic Community expanded the program. Milksheds increased from 18 to 136, and urban markets grew to 290. By 1985, 43,000 village cooperatives covered 4.25 million milk producers, and domestic milk powder production soared from 22,000 tons to 140,000 tons by 1989. Phase III, 1985-1996, focused on expanding and strengthening dairy cooperative infrastructure. Veterinary health care, feed, and artificial insemination services were extended to cooperative members. More emphasis was placed on research and development in animal health and nutrition. IDC and NDDB were merged, granting NDDB national importance and operational autonomy. This phase ensured the sustainability and growth of India's dairy sector. Today, India boasts over 133,000 village dairy cooperatives, federated into 177 milk unions and 15 federations. These cooperatives procure an average of 25.1 million liters of milk daily, linking producers in villages with consumers in more than 700 towns and cities. The national milk grid bridges seasonal and regional variations, ensuring fair returns for producers and quality products for consumers. NDDB's future focus includes strengthening cooperative business, enhancing productivity, improving quality, and building a national information network. Milk comes in various forms, each serving different purposes and consumer preferences. These include market milk, pasteurized milk, sterilized milk, homogenized milk, soft-curd milk, flavored milk, vitaminized milk, irradiated milk, mineralized milk, and frozen concentrated milk. Fermented milk varieties such as natural and cultured buttermilk, acidophilus milk, and yogurt are also popular. Standardized, reconstituted, recombined, toned, double-toned, and humanized milk further diversify the market, catering to nutritional and processing needs. India is the world's largest producer of milk, with annual production exceeding 120 million tons. The country has 3 times as many dairy animals as the USA, mostly kept in small herds of 2 to 8 animals. However, the annual milk yield per animal is much lower than in developed countries. Regional variations in milk consumption are significant, with Punjab and Haryana leading, while states like Orissa lag behind. Despite these challenges, India became the world leader in milk production in 2001-02. India's rise in milk production is mirrored by global trends. In 2008, the USA led with over 86 million tons, followed by India, China, Russia, Germany, Brazil, France, New Zealand, UK, and Poland. The world's total milk production reached nearly 578 million tons. Per capita milk consumption varies widely among countries, with Israel and Pakistan consuming much more than India, Bangladesh, or Japan. These statistics highlight both achievement and areas for improvement in the dairy sector. Milk is a complex food, containing all essential amino acids, calcium, phosphorus, and vitamins vital for bone formation and overall health. It's rich in vitamin A, D, thiamine, and riboflavin. Though deficient in vitamin C, milk fat provides energy and essential fatty acids, while lactose aids digestion and energy supply. The composition of milk varies by species and breed, affecting its nutritional value and processing characteristics. The composition of milk depends on several factors, including species, breed, interval and completeness of milking, disease, stage of lactation, yield, feeding, season, age, and health of the animal. For example, buffalo milk has higher fat content than cow milk, while human milk is richer in lactose. These variations influence the processing, nutritional value, and suitability for different dairy products. Milk is a rich source of energy, with milk fat providing 9.3 cal-G, protein 4.1 cal-G, and milk sugar 4.1 cal-G. Typically, 100 grams of cow milk delivers 75 calories, while buffalo milk gives 100 calories. These values are crucial for dietary planning and understanding the role of milk in nutrition, especially for infants and growing children. Colostrum, secreted during the first 3 days of lactation, is vital for newborn calves. It contains high levels of immunoglobulins, providing antibodies essential for immunity. Colostrum is also rich in iron, copper, fat, protein, lactose, and vitamin A, making it indispensable for the health and growth of young animals. Boiling milk causes several changes: reduction in cream percentage, decrease in curd tension, protein decomposition, enzyme destruction, darkening of color, coagulation of albumin, cooked taste, precipitation of calcium and magnesium salts, and breaking up of fat globules. Sometimes stone formation occurs during heating, affecting both quality and processing equipment. Stone formation, or fouling, occurs when milk is processed without prior heat treatment. At low temperatures, soft, curd-like deposits form, restricting flow and increasing pressure. At high temperatures, hard, granular deposits with high mineral content interfere with heat transfer. The amount of fouling depends on milk pH and composition and can be mitigated by adding pyrophosphates. Understanding milk's density and specific gravity is essential for processing, adulteration checks, and designing storage structures. Cow milk has a density of 1.028103, buffalo milk 1.031032, and skim milk 1.035137. Despite higher fat in buffalo milk, its specific gravity is greater due to higher solids, not fat, SNF. Lactometers are used to measure specific gravity, with corrections for temperature. A lactometer is a hydrometer used to test milk's specific gravity, helping detect adulteration and monitor changes during processing. The Quevin scale is used for readings, and corrections are made for temperature differences. Additional tests for fat content are necessary for comprehensive quality assessment. Other hydrometers measure alcohol, sugar, and battery electrolyte strength. Total solids and solids not fat (SNF) are determined using the Gerber method. These values are crucial for assessing milk quality and suitability for processing. For example, milk with 3% fat and density of 1016 kg/m3 yields 8.38% total solids and 5.38% SNF. These parameters influence product yield, nutritional value, and processing efficiency. Milk's freezing point is lower than pure water due to dissolved solids, making it useful for detecting adulteration. Fresh whole milk freezes at -0, 506 degrees C to -0, 504 degrees C, while buffalo milk freezes at -0, 549 degrees C. Boiling point is slightly higher than water, around 105 degrees C, and increases with concentration of solids. These properties are important for processing and quality control. Specific heat and thermal conductivity of milk vary with fat content and temperature. Whole milk has a specific heat of 3.89393 kJ/kgK, while skim milk is slightly higher. Thermal conductivity is calculated using Lamb's equation, which helps design efficient heat exchangers for processing. These properties are vital for pasteurization, sterilization, and other thermal treatments. Milk is naturally acidic, with cow milk having 0.13014% acidity and buffalo milk 0.14015%. Developed acidity results from bacterial action on lactose. pH values range from 6.466 for cow milk and 6.768 for buffalo milk. Higher pH indicates udder infection, while lower pH signals bacterial activity. Monitoring acidity and pH is essential for quality and safety. Milk's viscosity affects processing, storage, and heat transfer. Whole milk's viscosity decreases with temperature from 2.79 at 10 degrees C to 0.68 at 80 degrees C. Viscosity increases during concentration, homogenization, and aging at low temperatures. Milk forms can be categorized as Newtonian or non-Newtonian fluids, influencing equipment selection and processing methods. Surface tension influences milk's behavior during processing, such as droplet formation and foaming. Cow milk has a surface tension of 52 mmnm, while buffalo milk is slightly lower. The color of milk ranges from yellowish creamy white to bluish or greenish yellow, depending on breed, feed, and fat content. Greater intake of green feed deepens the yellow color. Milk's refractive index helps detect adulteration, with cow milk at 1.3461 and buffalo milk at 1.3477. Flavor is a blend of smell and taste, influenced by lactose, minerals, proteins, feed, season, and handling. Abnormal flavors can result from bacterial growth, foreign materials, or poor sanitation. Maintaining flavor is crucial for consumer acceptance. Gentle but complete agitation is necessary for dairy products containing butter fat. Severe agitation causes clumping and churning, while insufficient agitation leads to localized overheating. Milk expands when heated, especially if air is entrapped, affecting tank capacity and processing efficiency. Overrun measures the amount of air incorporated into whipped or frozen products, impacting texture and quality. Foaming occurs due to surface activity of solutes in milk. Pure liquids do not foam, but proteins and other constituents can create persistent foams. The degree of foaming affects processing, product quality, and equipment design. Understanding foam formation helps optimize processes for products like butter, ice cream, and cheese. Flowcharts represent the sequence of operations in dairy processing, aiding in understanding, monitoring, and equipment selection. For example, preparing dried vegetables involves sorting, washing, peeling, slicing, and drying. Flowcharts help identify critical control points and improve process management. Equipment required varies by product, ensuring efficient production and quality control. Flowcharts for milk processing include pasteurized milk, sterilized milk, flavored milk, buttermilk butter, ice cream, cheddar cheese, cottage cheese, and evaporated milk. Each chart outlines steps such as sorting, heating, cooling, fermenting, and packaging. These visual guides are essential for training, process optimization, and ensuring product consistency. Milk is received from producers or collection centers in cans or bulk containers. The first stage involves emptying cans over tip tanks, weighing, and recording consignments. Milk is then pumped through coolers to storage tanks. Mechanization includes power-driven conveyors, automatic tipping, and can washers. Bulk milk reception involves preparing to unload, weighing, and measuring, using sanitary meters and load cells for accuracy. Milk transport tankers have capacities over 12,000 liters, featuring stainless steel shells, insulation, and necessary fittings. Safety, temperature, and agitation are key during unloading. Agitation ensures uniform butterfat distribution. Storage tanks hold raw, pasteurized, and processed products, maintaining temperatures below 7 degrees C and ensuring sanitation. Tanks are designed for cleaning, inspection, and foam-free filling. Milk silos can hold 50,000 tons, optimizing space and efficiency. Agitation prevents cream formation, with propeller agitators preferred. Refrigerated storage tanks cool milk to required temperatures, using jackets for chilled water or refrigerant circulation. Processed tanks treat products like butter, cream, and yogurt, while aseptic tanks store UHT processed milk between sterilization and packaging. Pasteurization heats milk to predetermined temperatures, killing objectionable microorganisms and improving preservation. Developed by Louis Pasteur, the process ensures safety, flavor retention, and extended shelf life. Standardized methods include long-hold batch, HTSD, and UHT pasteurization, each balancing bacterial destruction, taste, and processing efficiency. Long-hold or vat pasteurization is a batch method, heating milk at 63 degrees C for 30 minutes. Rapid heating, immediate cooling, and gentle agitation are key for success. Advantages include suitability for small plants and cultured products, simple controls, and low installation cost. Disadvantages are slow process, manual controls, and higher heating and cooling expenses. High temperature short time, HTSD. Pasteurization uses plate heat exchangers for continuous flow, heating milk at 72 degrees C for 15 seconds. Regenerative heating reduces energy costs, while controls for flow rate, temperature, and pressure ensure uniform treatment. Advantages include economic operation and precise temperature regulation, though the system is complex and costly to install. Ultra-high temperature, UHT, pasteurization heats milk at 88 degrees C for 3 seconds, offering better texture and greater bacterial destruction. Equipment is similar to HTSD units, but operates at higher temperatures and shorter holding times. UHT treatment is often used for products requiring extended shelf life and improved body and texture, such as ice cream. Sterilization heats milk above 100 degrees C to kill almost all bacteria, allowing storage at room temperature. Conventional methods package before heat treatment, while UHT or aseptic methods package after. Batch retorts, water spray retorts, rotary batch sterilizers, hydrostatic retorts, and continuous rotary retorts are used, each with specific advantages and challenges. UHT sterilization treats milk at 135-150 degrees C for a few seconds in continuous heat exchangers. High pressure prevents boiling and fouling, ensuring efficient heat transfer. Plate heat exchangers are commonly used, requiring sophisticated gasket materials. Direct steam injection systems rapidly heat milk, with precise control needed to maintain product quality and volume. Evaporation removes water from liquid food, concentrating products and reducing storage, transport, and packaging costs. Types of evaporators include natural circulation, short tube, long tube, forced circulation, agitated thin film, centritherm conical, and expanding flow evaporators. Each type is suited for different products and operational requirements, optimizing heat transfer and residence time. Mass and energy balance in evaporators is essential for efficient operation. During plots and empirical equations help calculate boiling point rise and latent heat. Factors affecting heat transfer include temperature difference, fouling, boundary films, and energy expenditure. Selecting the right evaporator depends on capacity, concentration, product sensitivity, cleaning ease, and cost. Homogenization breaks up fat globules in milk, preventing cream separation and improving texture, viscosity, and digestibility. The process uses high-pressure pumps and minute orifices, reducing fat globules to below 2 microns. Homogenized milk is recommended for infants and used in products like evaporated milk and ice cream. Proper dispersion and steady pressure are crucial for efficiency. Homogenizer consists of a pump, homogenizing valve, breaker ring, tension spring, and valve seat. The valve is the heart of the machine, breaking up fat globules through shear and disruption. Two-stage homogenizers improve dispersion and control viscosity. Proper maintenance, including valve resurfacing and pipe condition, ensures consistent product quality and efficient operation.